80% of the weights, and then they lost this much of accuracy. So the more you prune, the more you're losing accuracy in terms of like what you learn, losing it. So then, to actually try to recover from this pruning process, there are like quantization-aware training. You can have pruning with fine-tuning. So you prune and try to train the model a little bit so as to try to gain the loss, to regain from what you lost. So you can see that by slightly fine-tuning this model, you can recover the accuracy. So that now, even with 90% of pruning, you still have some accuracy. So this is trying to keep this accuracy as high as it was before. So you see, by 80%, you have the original accuracy, but in this case, you can only prune by 50%. So this is another table to show the results of pruning. So some models were compared before and after pruning. So in this case, we compare two parameters, the memory, the reduction, as well as the computation in terms of multiplication and accumulation operations. So you can see that we are in these models after pruning, the models actually have significantly reduced in terms of size, in number, and this is the reduction and a relative reduction, as well as how we have reduced in terms of computation. So basically, this is like a direct relation. So the more you prune, the more you reduce in terms of size and multiplications that you have to perform. So how we formulate then the pruning process? So pruning can be formulated as an optimization process or problem. So given that you have these model parameters, we are trying to seek a sparse version of the matrix that retains only the most important parameters. So this can be formulated as an minimization problem, where we are trying to minimize the loss of pruning these weights given the input. As well, we are trying to use n as a threshold of how much weights we are going to prune. So n is like how many numbers of zeros you have to retain, like how many, this n, meaning like how much you're going to basically prune. So you are limiting the number of zeros you want on the model. So if you formulate this as an optimization problem, then you can find the appropriate pruning ratio. So then how do we prune? So in terms of granularity, we can, this is like in which pattern are we going to prune? So if you have a dense weight matrix on our left, so we can either prune it randomly or unstructured. So we will actually be getting exactly the less important weights and then pruning them. But again, we can also confine ourselves to a pattern. So in this case, you can say you're only pruning an entire row and not just any random, because the two actually differ in terms of flexibility. So fine-grained or unstructured pruning is very flexible. And also that in terms of the irregularity in the weight matrix, it's very hard to formulate. Now, if you have all these zeros scattered all over in our weight matrix, then for you to really get from the acceleration, then you have to know exactly where these zeros are. And if you locate them, then it's more of a challenging task to accelerate. But when you know that a certain row is zeros, it's much easier to accelerate this. But again, this is like this is more accurate than this. So we'll see. This was supposed to be structured. So we can also have different other dimensions of pruning, because in a neural network layer, a convolutional layer, we have 4 dimensions. We have the filter dimensions, where we have the height and width, and we also have the output channels, which is also the same as the number of weight filters we have, and the input channels. So in either of these dimensions, you may choose where to perform pruning. So this means that you really have a high search space in terms of where exactly you're going to prune. So for this, then we have more pruning granularities. So in a fine-grained pruning, you just do, as we said, you use no particular pattern. Then in pattern-based pruning, you can have a certain pattern that is more regular. And then you can now using the dimensions we mentioned, you can now prune a vector. So just say you are removing a certain number of rows. You can also prune the filter itself. You can entirely prune a filter so that you have less filters of the weights. And then you can also filter the channels. So basically, this is like choosing from which dimension you can filter. And also you can also mix up, you can prune a filter, you can also, in the remaining filters, you can also use a certain pattern to prune. So you have really high search space in terms of pruning. So for example, of course I said the hardware has to support the kind of pattern you choose. And for this case, the like NVIDIA hardware actually have a certain support for sparsity. So they introduced this NM sparsity, which means that for every contiguous M elements, you can then prune N of them. So in this case, the classic case is the 2 to 4, which is 50% sparsity. So for every 4 bits, you can prune 2 of them. So they have like embedded this support in their hardware. But now, if you have a different pruning strategy, then you have to consider the support in hardware. So some other cases, as we said, there are various levels of granularity in, for instance, the channel pruning. So if we have these layers, these 4 layers, 5 layers, we have a number of channels, then you may decide to prune a certain number of them, and then you can have different pruning ratios. Pruning ratio being the ratio of how many channels you prune from the total. And so we can have different sparsity levels in different layers. So like mixed precision quantization essentially. And then how do we know exactly which neuron or which connection to prune? So we know the granularity, you can choose per channel, but how exactly do you know which neuron to prune? So it's to find the less important parameter. And in this case, there are also different techniques to do this. One of them is magnitude-based pruning. So in this case, you consider weights with the largest absolute values to be more important than the others. So if your value is bigger, then you consider it like more important. If it's small, then yeah, of course, that can also not be true, because as we said, some cases where you have small values mean that they are more important. But again, this is just one of the methods. So you can use an LP norm formulation to prune certain values so that you have a prune weight. There are also others. you can use just a pruning ratio. For example, if you are pruning channels, you can say randomly prune 50% of the channels. And then you can also have more other techniques like regression-based pruning, where you minimize the reconstruction error. So where you consider how much error you incur by pruning a certain weight vector. So you can minimize that error, then find how to prune it. And then there are also these others. So the normal way of doing it is in the practical, like how they do it in research. For example, is first to analyze the sensitivity of each layer, because some layers will be more sensitive to pruning than others. So you can prune a certain layer and then plot this from one layer to the next and observe the accuracy. So for example, this is layer 1. So you pick through all the layers, and then you will notice in which layer do you use more. And then from there, you can just find a balance or a threshold of the pruning ratio that tries to preserve the accuracy. In this case, you can see 70 seems to be the best in this case. So really, it will actually need maybe sometimes have a machine learning expert to do this, to be able to find an efficient neural network. So to break this up, of course, what if we have something like automatic and you just press a button and then you have a neural network that's more efficient? And this is actually one of the objectives with the sessions that we will have in the afternoon about neural architecture search and knowledge distillation. But even in pruning, of course, you see we have really a large design space, because we have all these dimensions that we can prune. So, and we really do not have like a more clear technique of how do we know which neuron to prune. In fact, there was a paper that was talking about like why there is so much confusion in pruning, because there is no clear methodology to know where to prune. So there's also this concept of the lottery ticket hypothesis. So this one tries to formulate and suggest that that massive models actually may not be necessary to start with, but you can have actually in this large network, you can have some sparse networks that they call winning tickets, that you can extract a model from a large ticket, a large neural network that you don't even need to train. But if you pick it and then you train it in its small factor, then it's as accurate as the bigger one. So this is just some formulation that they suggest this. And they did a practical example where of a 90% pruned model called the BAT will retain 97% of its performance. And it will be able now, because it's small, it can train 5 times faster. Yes.
Sorry, how we can find this subnetwork?
So how to find this subnetwork? So I think this is one quick, for the lottery ticket, actually they did it randomly. They say you randomly initialize a weight and model and have several of them, then one of them is going to be more efficient. But I think this can be better explained using neural architecture search. Yeah, I think because this to me is from my understanding that it was like more of a way of introducing neural architecture search in Pruning. Yeah. Okay, and then the other way of doing pruning is to perform it as a reinforcement learning problem. So what we will usually do, as we said, is like an iterative process. You prune and observe the accuracy, prune with a different pruning ratio, and then observe the process. And then now, what if now you make this automated using another model, or another algorithm, so that now the algorithm will be observing the accuracy as it alters the pruning ratio. So more of like a reinforcement learning method. And so with this one, then at the end of that process, we'll be observing the error as well as all the parameters. So this can be more automatic than doing it manually. Because really you have too many options of pruning areas. So then, of course, because it's iterative, as you iterate, you may be losing losing accuracy. So what you usually do to regain what you lose, at least to some extent, is to fine tune. So as you prune and then you retrain. Basically, the training process, but using fewer data sets. So you're just simply retraining it, but maybe with less rounds than you do the normal training. So this is simply to prune and then train it a little bit and see if it's getting better. Of course, it's quite an iterative process. So to show that how this like really works on efficiency, for example, this full dense matrix. So you are doing a convolution between the input and the output. You are basically doing 9 multiplications for one output pixel. But if you prune, then you have, for example, 2 values left after pruning, then you're only doing 2 matrix multiplications. So this is like how you gain from sparsity. And it is just the importance of like what the gains we get from pruning. One, from the storage perspective, because now you are storing 2 values. But again, this overhead, because you need to know where these 2 values are in this vector. So you usually have encode this sparse data. That is why the regular pruning was more advantageous, because being regular, you can easily encode that into a compressed representation. So sparse, like regularly pruned models are easier to handle than the irregular ones. Yeah, so the pruning actually is like basically very short in its concepts. So that is the end of the presentation. So probably I will show you some code on both quantization and pruning. So are there any questions on this?
So is there some relation between pruning and explainability?
Okay, yeah. So that's an interesting question, because as I said, it's like a lottery, you see. Like you are just pruning. Okay, the criterion for pruning is not very clear, and that is what it was they found in some of the papers. They try to see this pruning as quite of a random process that is not really explainable. You cannot figure out exactly which neuron. You cannot really justify that this neuron was less important. But again, it was iterative and random. Yeah, so its explainability is.
I think it can be open to a research question for like how can put some ways to do other papers.
Yeah, so that's why there was a paper that they were like saying why so much chaos in pruning. It's not quite explainable. Of course, in quantization, it's really straightforward. It's mathematical, but in pruning, it's quite unclear. So I'll just switch maybe. So we have prepared some notebooks that we will share. So what I will do, because I try to make them be able to run as fast as possible. But even so, it takes time. So I will just try to walk you through the notebooks so that later you can have them and play with them.
Even like if your laptop's running, you can go to the link and run the notebooks within the notebook folder and follow along with OBED if you like.
Yeah, so these notebooks, you can run them using VS Code. You can actually run them on Google Colab. It's much easier if you use Colab because you do not have to install any of those libraries. Yeah, so and then in this repository, you will find all the slides and
It would be better if you could like just show them a little bit about how to run it on the Colab. Just
yeah, sure. So I will basically, yeah, let me show you this. So I am trying to use the VS Code. And so let me just open the repository so that. So you'll find the notebook.
You have to share the screen here. Understanding.
Yeah, so in this repository, you find the slides and the notebooks. So in these notebooks, probably once if you go to Google Colab, actually you can link the GitHub. So you can open a notebook and then here you can use GitHub and link this to the GitHub, and then we'll find the notebooks. For example, in this case, okay, let's start with quantization. So then now you're able to run this from Google Colab. Normally you can connect to runtime, either you can use the GPU or a CPU. Okay, so first notebook is on quantization. So we try to explain like the basic concepts of the uniform quantization that we explained. We also run the post-training as well as the quantization aware training on a very small CNN. And then we compare the accuracy and the size trade-offs. And then we also extend the custom to a custom straight-through estimator that we can use to do quantization aware training. So in the setup, if you were to like, these are like the libraries you will need, you will install them in your local host. But in Colab, you just run these cells. So part of the notebook, we provide some helpers. So these are just functions to help you evaluate the model's performance after you train or after you do quantization. They're just ready to use. And then I have some function to plot the weight histograms for after quantization. And then for us to load, to do any training, we need a data set. So in this case, we are using CIFAR10 as a small image classification data set with 10 classes. So the first module in this notebook is to how to formulate the quantization and visualize that. So we try to visualize this using a matplotlib plot, and we actually know the formulas that we had in the slides are like implemented using this thin quantization. And then, so because of time, maybe if I try to run this, it may take some time. So I will just use these outputs that I did when I ran this. So you can see that if you try to, it's more of like a staircase quantization process where we have this symmetric integer 4, where we can use 4 bits to quantize an input range from -1 to +1. You can see for 4 bits, this is the resolution we have. If you use less bits, you can see the step size is larger, and this means your resolution is poor. So this is the sign quantization that we talked about. I'm finding it difficult to navigate this.
If you can turn off the Teams, you can edit Teams so that messages come.
Notifications. Okay. So in this, the next module is that we define a small network. Usually when you are trying to train a model, you have to prepare the inputs. So there are transformations you have to do to the input model, to the data set, and then you download it, and so you download it to a certain folder, and then let me just use my VS Code because it's very hard to navigate the color. So yes, so you do the transformation. This is just standard reprocessing, and then we visualize some of the images that we have. It's a 10 class data set. So here we take a network with like how many layers? Like we have 1, 2, 4, 5, 6 layers. So it's to classify these 10 classes of images. So you will notice that there are 2 stubs. So you are using the torch, okay, PyTorch. PyTorch provides some quantization utilities. So before you quantize, before you begin running this, you have to quantize the inputs. So they provide a quantization stub. So this stub is like the first step to quantize the input, so that when you get into the model, you have quantized inputs, and at the end of the model, you have a dequantization stub, so that you quantize it back to the floating point. Just the definition of the model. So when you train for one, you train this model, let's say it's we used 5 epochs, and again, this is a very small model, so our objective was not find the best accuracy. We just wanted to find some trained model, so we get some accuracy of 69%. This latency is just basically for the GPU, but it's not important. But in real hardware, then we will have to monitor this. So this model is 4 megabytes of weights. And if you try to plot some of the distributions in this model, as we said, you can see some layers have different distributions of weights. So for example, this layer has this normal distribution. Some layer has this kind of distribution. Some has this. And so then right now, you can see that if you use, ideally we will use the same quantization parameter for all. But again, that is not fair because you can see that in this layer, most weights are within a smaller dynamic range. But in some other layers like this one, you see it's covering a wider dynamic range. So the ideal situation of quantization here would be to use mixed precision so that in this layer, you have a format that is more, that accepts a larger dynamic range than this, so that you are able to represent this more accurately. But again, because of quantization aware training, then you can train the model so that at the end of the training, then we have a more uniform quantization training. And the one thing I didn't cover in the advanced quantization technique is a method we call weight equalization. So you try to make all the distributions in the various layers equal. So there's a mathematical formulation of balancing the distribution of weights from one layer to another, so that they at least have a similar distribution. But that is also another advanced technique in quantization. So once you have this, I also try to use one modern model which is called mobile net. So like a more deeper network that is trained on ImageNet. ImageNet is like a very big data set that has 1,000 classes. So for you to use the same ImageNet trained model, you need to modify it a little bit to accept another model, another data set. So in this case, we fine-tune it. So I did provide this for reference so that if you wanted to retrain this using MobileNet, you can do it. So the first process we do is post-training quantization of the small network that we designed and trained. So here you can read the references that are in the Python documentation. They try to explain their functions and how to use this library to do quantization. So you will see various implementations. And one aspect that you need to understand is that, of course, once you are quantized, you are targeting a certain hardware. And this Python has provided two kinds of hardware. There's that is optimized for Intel and CPU for the desktop. And then there's also QNN when you are targeting smaller devices like the ARM mobile or CPUs in Android, iOS. This is for mobile deployment. So just for inference. So here we try to do post-training quantization of our small network. So when I did this, you remember the accuracy before was 69 around there, and then because of this small model, we didn't lose as much accuracy. It's like, in fact, it stays 70, which is higher than 69. Basically meaning after post-training quantization for this particular model, we did not lose anything. So meaning actually, in some cases, as we said, 8-bit quantization is as good for some applications. But if you try to do the same for some models like MobileNet, actually in this case, I did this here. We can see for MobileNet, with integer 8 post-training quantization, the accuracy drops to 10%. So it depends on the complexity of the model and its data set. So some models can preserve quantization and can preserve accuracy, while some will significantly lose accuracy. So in this MobileNet version 2, lost accuracy to 10%. This means it's actually unusable. So I plotted for this small network in comparing the accuracy drop, but actually not drop. But for MobileNet, it lost accuracy. So you can actually try to plot all this together. So then here I model the quantization aware training for the small network. So we are again using the provided converters and functionality from PyTorch. It has like libraries or functions to do quantization aware training. So here we do a quantization aware training, and you can see the accuracy. In fact, okay, because of this, it was a very small one. And I only trained it for a very short time. It was like it even dropped to 65. Meaning we actually destabilized the network. But in this process actually works better when you are doing it a larger model. So this actually shows that again, in some cases we may not need quantization aware training. We would only simply need post-training quantization. So later I tried to define out the standard, the state through estimator that you can use to quantize a model, to perform quantization aware training model by yourself. So I have defined the state through estimator function. So you can see that during the backward process here is where you just use the gradient output directly. As we said, we are trying to make it transparent. But in the forward, we do the quantization of the forward pass. And then you use this in defining a quantized layer and a quantized evolution. And then I defined the same small network using this quantization aware training modules. And so when you, and then trained using different bits, and the result, as you will see here, are that, as we saw before, the small network for post-training quantization, we retained the accuracy. But for the small network, using this STE or the standard state through estimator, upon performing some quantization, of course, for lower bits, you can see the less the bits you use, the less the accuracy you get. So this is also like a demonstration on how many bits to use. So the less bits you use, the less accuracy you have. So this is just again a small example, but again, when it comes to real models, then you have to be more careful. This was simply a demonstration. And so this notebook is provided. You can just go and check it in detail. So, and then now to move to the pruning part, there's also a notebook for this case. So first we visualize the pruning itself. So here we have I provided a randomly generated tensor, and then you can prune it using sparse pruning, regular pruning, and irregular pruning. So unstructured and structured pruning. So here you see in an unstructured pruning, we have random locations of pruned weights, but for the structured pruning, we have like very systematic pruning. So we have like 2 columns removed, and this is more regular. So here we also prepare a model for pruning. It's also, we use a small model which is called the LeanNet model, which was the first convolutional neural network model. And then we use it with the MNIST dataset. So here we perform these 2 types of pruning, unstructured and structured. So again, we are using the utils provided by PyTorch. So you just tell it that I want 40% of the weights removed using just that pruning ratio that you give it. So as you can see, when you perform unstructured pruning, the original accuracy before training was 98.61, and then unstructured pruning after fine tuning. Okay, before fine tuning, it is 98.61. If you fine tune it a little bit, you get a little bit higher accuracy because you have like try to recover from the pruning. And then the global sparsity we have in this case is 40%. So this is unstructured pruning. But you will notice that if we do structured pruning, we actually lose more accuracy because of structured pruning, because you are restricting your pruning to a certain pattern. So here we have accuracy of 94, in respect to 96, that was the original ones. But again, after you fine tune, then again you recover from the loss. So then you have 98.75. So then what usually happens, the iterative. Now you make it a number of iterations. You can define the number of iterations to use one. And then in this iteration, then you will be reducing the pruning ratio iteratively. And I did a small iteration, and because it's really a small one, you can see that for every iteration, as you increase the sparsity, there are different accuracies. But again, because this was iterations with fine tuning, it was getting better a little bit. But you see, beyond a certain level, you will start seeing complete loss of accuracy. So that is how you use this. So this notebook are quite easy, and just to introduce you to this, and then you can scale them up to different levels. So these are provided, so feel free to use them, and it will just solidify the concepts we did in the presentation. Yeah, so that's it, unless there are any questions on this part. So this I think was quite fast, so I think we're supposed to proceed for a lunch break, right?
Yes, we can proceed towards lunch break, like we have some time, but we can have like some questions.
Yeah, so at the end of this pruning session, you had this graph
Yes.
with the sparsity and accuracy, and it's difficult to understand that higher sparsity can lead to higher accuracy.
Yeah, I think the problem with this, of course, I said in this sparsity, I was fine tuning as I pruned. And again, the challenge is that this model was very simple.
Actually, sometimes people also want to think that sometimes pruning can like be a benefit in these models if we have a big model. So some models can like overfit the data.
You see it.
Yeah, so when we are taking
Okay.
the weights from them, so it can like regularize, sort of provide regularization to the model. So like even removing the weights can even benefit the model more and increase the accuracy. Obviously, we are also fine tuning this iteration. So that's why it's increasing.
Yeah, of course. Yeah, again, it brings the other concept about deep learning. About there's also complexity of the model, overfitting, underfitting. Those are concepts that come into play because now if you're pruning, we're making the model simpler, but you're using the same data set. You easily overfit. But again, that's why this daily graph is not ideal. But if you were to have a more complicated, more complex, a deeper model, it will be more going in this direction. As we showed, but it was just to show that you can now change the model a bit and then see what happens.
Okay, so it's iterations more than actually.
Yeah.
Any more questions? So should we should we take a break then and come back at 1 o'clock? So
Yeah,
so we will proceed as planned. So at 1 o'clock we will start the topic of knowledge distillation, and I will be presenting that. So and in the meantime, if you have any questions or something, you guys can approach us, me or Wade. We can talk about that. But yeah, for now, then see you at 1 o'clock. Thank you so much.
Awesome.